In this video, we're going to be talking about the definition of a limit. A limit is an output. That's its most informal definition. But we need to get used to this idea of approaching values. So we can approach a given input. We can get closer and closer to plugging in a specific input. And when we do that, our outputs approach a specific value as well. And a good example of that is this function x squared, just a basic quadratic or parabola. As I'm plugging in inputs over here, they get closer and closer to 0. Let's say I plug in 2, I get 4. If I plug in 1, I get 1. If I plug in 0, I get 0. So as my inputs were approaching 0, my outputs were also approaching 0. Let's look on the other side of the graph. If I plug in negative values like -2, then I get +4. If I plug in -1, I get +1. And if I plug in 0, I get 0. So as my inputs over here on the left side were also approaching 0, the output again was approaching 0. So we can have these approaching values. I can plug in inputs that approach a certain input, and as I do that, my outputs also approach a specific output. So that's the idea of a limit, that y value or output value that is approaching. This is the notation of a limit. The variable c is just an input value, just an input number. So it's saying the limit of this function as x approaches a specific input, c. That value is the output that's approaching, and that's symbolized by a capital L. So whenever you're evaluating a limit, this is the notation you will see. For example, we'll go back to that x squared function. If I want to find out what my output is approaching, as my input values are approaching +1, this would be the notation. The limit of x squared as x approaches 1 is 1. That's the output. And let's see why. If I get really, really close to 1, approaching it from the right side here, I could plug in 2, I could plug in 1.5, I could plug in 1.1, and I can get closer and closer, 1.01, 1.001. And as I do that, I'm evaluating those inputs by squaring them. My outputs are also approaching that output value of 1. If I do the same thing from the left side, or the more negative side, or the lesser side, I'm approaching 1 from the left, so I'm plugging in 0, I'm plugging in 0.1, 0.5, 0.9, I'm getting closer and closer to 1, I'm plugging in 0.99 and 0.99999, I can do that all day long. But then I would compare my values in my output table, and I would see that my outputs, even though I'm plugging in lesser values of 1, are also approaching 1. So as I approach it from the right side, my inputs from the right side, or the greater side, or if I plug in inputs that approach from the lesser side, or the left side, then my inputs are approaching 1 from both sides. And when I do that, I get an output that approaches a given value. A limit value is not necessarily the defined value of the function. I'm not plugging in 1 specifically. My limit is what I'm approaching. So as I plug in values that approach 1 without actually plugging in 1, then what are my outputs approaching? And we'll see why that makes a difference. We can have one-sided limits. So as we just saw in that last table, I was plugging in values to the left of a given input, or lesser values, or more negative values. And when I approach from the left, we use a notation, a little negative sign next to that approaching input value. In contrast, when I approach from the right, I use a little symbol with a plus sign because I'm doing values that are more positive, or we could think of values that are slightly bigger than the value I'm approaching. A more complicated graph makes this idea a little bit clearer. So if I want to evaluate the limit of this function, of just this graph, as x approaches 2 from the right, what is my output approaching? So as I'm plugging in 4, my output is undefined but approaching 2. If I plug in 3, my output is about 6. If I plug in 2.5, here's my output. So I'm really tracing this graph on the right as I approach an input of 2. And if we just trace that graph all the way until we almost get to 2, we're just approaching an input of 2. My output is approaching and getting closer and closer to 5. So even though it's undefined, if I plug into, the limit is saying what is our output approaching. So it's getting closer and closer to 5. So the limit of the function as x approaches 2 from the right is 5. Let's do a left-sided limit. If I want to evaluate the limit of this function as x approaches -4 from the left, so I'm plugging in -5, plugging in -4.5, -4.1, I'm getting closer and closer to an output of 3. We're just tracing this graph on the left side as we approach -4, and our output is approaching +3. So that brings us to the formal definition of a limit, which says that the left-hand limit and the right-hand limit both have to be approaching the same value, or they both have to be equal. And that is when we have a true limit, not just a one-sided limit, but a both-sided limit, if you want to say that. So let's see why we have a limit and why we don't have a limit sometimes. If I want to evaluate the limit of this function again, as I approach -1, not just from the left side, but also from the right side, that would be symbolized by not using a one-sided limit symbol. If you don't see a one-sided limit symbol, you're always approaching it from both sides. Let's see if it exists. So if I approach -1 from the left, I'm tracing this graph, and my output is approaching +4. If I approach it from the right, tracing this graph, plugging in, getting closer to an input of -1, my output also approaches 4. So from the right and from the left, my output was approaching the same value of 4. Whether or not it's actually defined at -1, it's just what are they approaching and getting closest to from both sides. So since they're both approaching an output of 4, we say that the limit exists because the left-handed limit, or the left-sided limit, is equal to the right-sided limit, or right-handed limit. So in order for a limit to exist, that has to be true. Both sides have to approach the same value. Let's see what happens when it doesn't exist. So if I want to approach 2 from both sides and evaluate that limit, +2 from both sides, tracing the graph here on the left side, plugging in values that approach +2 and getting an output that approaches -1. If I try it from the other side, from the right side, plugging in inputs that approach 2 from the right side, my graph or output values are approaching +5. So because the left-handed limit of -1 and the right-handed limit of 5 are not the same value, then we say that the limit does not exist because the left-handed limit does not equal the right-handed limit. So there's an introduction to limits and evaluating them graphically.